Hello, Mr. Kitchen, Cobleskill, Richmondville High School of Physics. Today we're going to talk about the application of impulse and momentum. And if you recall, J is the symbol that we use for impulse, that's force and time, and this is delta P, or change in momentum, typically mass times change in velocity. The first application that I'd like to take a look at is if you want to increase the momentum of an object or increase the speed of an object. And you know, if you've played any sports or even in gym class, they tell you when you throw an object, a football, a baseball, a discus, a shot put, it's important for you to follow through. And you might think, like I often did, why is it important for you to follow through? Once the object has left your hand, there's no way that you can influence the path of that object. Well, we can look at it through the application of impulse and momentum. Let's say you don't follow through. This is the amount of force that you can apply, and you're going to do that for a certain amount of time. You'll end up with an m delta v, a change in momentum of, and I'm just saying the ball over here, although it could be whatever object it is that we're throwing. If we do follow through, the deal here is that we're just trying to increase the amount of time that your hand is in contact with the ball. And if we can increase the amount of time and we can still apply the same amount of force, the product of these two has to be larger. Now the mass of the ball isn't going to change, and that means its velocity has to be greater. So if you can push on a baseball for an extra 30%, you can make that baseball go 30% faster. Okay. Same thing applies to golf and football and many, many other sports. Now, another way to look at impulse and momentum is, let's say you're trying to design something to decrease the amount of force. For example, airbags do this. We'll talk about airbags in cars, but stuntmen also have airbags as well, and they work exactly the same way. If you don't have an airbag, then you're going to have a certain amount of force, but it's going to act for a short period of time. Think if you're not wearing a seatbelt and you don't have an airbag in your car, there'll be an inertia that you have, and you're going to go forward, and they're going to have that second crash inside the car when you contact the steering wheel or your head contacts the windshield. There's going to be a large amount of force for a small amount of time. The Institute for Highway Safety always figures it only about 1,000th of a second for you to come to a stop when you hit that steering wheel. Well, that force and time has to negate your momentum over here, whatever your mass is and how fast you're traveling. However, if you do have an airbag, you're going to hit something soft. And it's not so important that it's soft. What's important is that you don't stop right away. It's going to take you a while to slow down, and so the amount of time is going to be increased. We can't do anything about this part of the equation. Your momentum is going to stay the same, but a larger amount of time is going to lead to a smaller amount of force. If you can increase the amount of time that it takes someone to come to a stop by a factor of 3, you'll decrease the amount of force on that person also by a factor of 3. Now here I want to talk about elastic and inelastic collisions, and I know this is kind of a busy slide, but let me take you through it. This is supposed to represent an unyielding wall. You can think of it as a brick wall or something like that. And we're going to take a look at two kinds of collisions here. On the top, we've got elastic collisions, and on the bottom, we're going to take a look at inelastic collisions. Now, in an inelastic collision, we can think of inelastic collisions as being sticky collisions. So I've started out, say, here with a lump of clay. And that clay has a certain amount of mass, and we're saying it's moving forward with V initial equal to, and we'll give it a positive direction because it's moving to the right. Now that clay, when it hits the brick wall, is going to splat and come to a stop, so its final velocity is 0. If we come over here, we can calculate the change in velocity. Delta V, delta anything, is always the final minus the initial. So our change in velocity is going to be, well, the final is 0, minus the initial, which was V sub I, is going to give you negative V sub I. So when we calculate the momentum change of that piece of clay, we have m V initial. And we can put the negative sign in there if we want as well. Now, on the other hand, let's contrast that with an elastic collision. And we might think of this as a super ball or something that's really bouncy. Also, it's still moving forward with a V initial equal to plus V, but this time it hits the wall and it bounces back. Its final velocity isn't 0, but it is negative V. And as we said, this is our elastic or our bouncy collision. When we go over here and we calculate the momentum, the change in velocity is going to be v final minus v initial, but our v final was negative v minus the v initial over here is minus 2 times the velocity. So when we calculate the momentum, we've got to bring, well, we can bring the negative sign down there, and it's 2 m delta v, all right, or twice the amount of momentum. So one of the important outcomes that we're trying to show you here is that when something bounces back, it transfers twice the momentum of something that sticks. So if your goal is to transfer momentum to something, to increase the velocity of that object or to decrease the velocity of that object, you're going to do it much more effectively if you can hit it with particles that bounce off as opposed to hitting it with particles that stick.